The types we've looked at in OCaml so far have been what we call atomic types. Types like integers, floating point numbers, and truth values that are individual values that can't be decomposed into parts. Where data starts to get interesting, though, is when we start to combine data into data structures. For us to be able to use data structures in OCaml, we first need to be able to construct those data structures from their individual parts using what's known as a value constructor. We'll also want to be able to describe what type these data structures have using what's known as a type constructor. And then, once we have a data structure, we'll want to decompose the structure to get at the individual parts using a technique called pattern matching. There are a few different structured data types in OCaml that we'll take a look at, starting with the tuple. A tuple is a fixed length sequence of elements. Imagine, for example, we wanted to pair together an integer and a Boolean value into a single value. To construct a tuple, we can use its value constructor, the comma. Writing 3, true creates a tuple value that stores the integer 3 and the truth value true. So what's the type of this value? The type isn't just int or bool, since this isn't just an atomic type. It's a composite type that contains both of these values. To describe the type, we can use the type constructor for the tuple, the asterisk symbol, which we read as cross. So the type of this value is int cross bool, and this type describes values that pair together an integer and a truth value. Other values of this type include 2, false, 0, true, and -1, false. All of these are tuples that share the same type. Notably, true, 3, or 3, true, do not have the same int cross bool type. The order of the values is important. So the value true, 3 has type bool cross int, which is a different type. And the number of values is important too. If there's a third value at the end, then the type would need to note that as well. For example, int cross bool. The parts of a tuple don't need to be atomic types. They could be other composite types as well. If we had the truth value true and the tuple 5, 1, we could put those two values together into a tuple true, 5, 1, and it would have type bool cross int. The extra parentheses in the value and the type here indicate that 5 and 1 themselves are paired into their own tuple. This value is not the same thing as true, 5, 1, which would be a triple of type bool cross int. They look similar, but they have a different structure. So now we have the ability to construct tuple values. We might define a value p, for example, to be a point in 2D space, represented as a pair of two integers. But once we have a data structure like a tuple, we need some way to later decompose the structure, to extract the individual parts from the composite structure. To do this, we can use a powerful technique known as pattern matching. Pattern matching allows us to match template patterns containing value constructors against the structure we're trying to decompose. A match might look like this. We use the keyword match followed by the expression we're trying to decompose. Then we can match it against one or more patterns. Each pattern is some value constructor that might contain variable names. Whichever pattern matches the expression first has its variable names bound to the corresponding parts of the original expression, and then the expression that follows the arrow after the pattern is evaluated to determine what the value will be for the entire match expression. Let's take a look at a specific example to make that clearer. We have this variable p, which is a pair of two integers. If we wanted to get access to those individual integers, we could write a match expression that matches the expression p. Then we need to define what pattern or patterns we're going to match it against. Since there are two values in this tuple, we can use the value constructor x, y here as the pattern we match against. The x and y are just variable names that we get to choose as the programmer. They could be any names. What's important is that this pattern, a pair of two values, matches the expression p, which is a pair of 5 and 1. So since this pattern matches, x will correspond to the value 5, and y will correspond to the value 1. Then after the arrow, we can write some expression that uses x and y. For example, x minus y, so that this entire expression evaluates to 4. Tuples only have one value constructor, so we only need one pattern here, but we'll later see examples where we might use multiple patterns in a match expression. Using this new pattern matching technique, let's try defining a function that takes a pair of integers and returns just the first one, something we might use if we only care about the x value in an xy coordinate pair. We would define the function as taking an int cross int argument, a pair of two integers. Since we want to return just the first integer, its return type will be int. Now we can match the pair against the pattern x, y to decompose the tuple into its two parts, and then return just the first value in the pair. This function now takes a pair of two integers as input and outputs just the first one. And since we didn't use the second variable name y at all, it's usually good practice to turn it into an anonymous variable instead, a variable that begins with an underscore. Starting the variable name with an underscore clarifies our intentions. It makes clear that the variable isn't meant to be used, which makes it easier to catch bugs where we wanted to use a variable but didn't. We can match more complex expressions too. Let's say we wanted to write a function to compute the distance between 2 points, where each point is a tuple of two floating point numbers. We need to deconstruct both points to get at the individual x and y values to compute the distance, so we could first match the first point, and then perform another match to extract the values from the second point. But this is unnecessary. We could just match the pair of both points at the same time. This is a tuple of type float cross float, cross float cross float. It's a pair of two values, where each value is itself a pair of two floats. So what pattern do we match it against? Since it's a pair of values, and each part of the pair is itself a pair, we could use the pattern x1, y1, comma, x2, y2. Again, we've chosen the variable names arbitrarily, but the important thing is that the structure fits the type of the expression we're matching. Now we have access to the individual x and y values for both points using a single match, and we can compute the distance between the 2 points. So far, we've only seen cases where we match an expression with a single pattern. It turns out that OCaml has some additional syntax features to make it easier to match expressions that only have a single pattern. For one, we can match directly inside a let expression. So we could equivalently say, let x1, y1, x2, y2 equal p1, p2, and then the expression to compute the distance. Here, we're matching inside the let expression itself. Instead of just a single variable name on the left side of the equal sign, we have an entire pattern to match against. We can even do this kind of pattern matching in the arguments to a function itself. Instead of using single variables p1 and p2 as the arguments to the function, if we know the function will need these values deconstructed, we can pattern match x1, y1 and x2, y2 directly in the function's arguments. These kinds of simplifications make code more readable, so be on the lookout for opportunities to use them. And recall that these simplifications only work when we're matching against a single pattern. That won't always be the case. For example, the next structured data type we'll take a look at is the list. While a tuple is a fixed length sequence of elements where the types of those elements might be different, a list is a varied length sequence of elements, and those elements must all be of the same type. We can describe the type for a list by adding the type constructor list after the name of the type of the individual elements in that list. For example, if we had a list of integers, its type would be int list. A bool list would be a list of truth values. If we had a list of pairs of integers, its type would be int cross int list. With tuples, we only had one value constructor for creating tuple values, the comma. With lists, there are two value constructors. The first value constructor is called nil, and it's represented as the open and closed square brackets. Nil represents the empty list, a list that contains no elements. The second value constructor is called cons, and it's represented as two colons. Cons takes two arguments, an element often called the head, and a further list of elements often called the tail, and it constructs a list whose first element is the first argument and whose remaining arguments are the second argument. Let's take a look at a few examples. Say we wanted to define a few int list values, lists of integers. We could construct an empty list of integers using just the nil value. But what if we wanted a list that had just one integer in it, the number 3? For that, we need to use the cons constructor. The head of the list, that is to say, the first element of the list, will be the number 3, which will be followed by the cons operator, and then the remainder of the list. But for a list with only one element, there is no remainder in the list after that first element. So the remainder is just the nil value for the empty list. So this expression now represents a list containing just the number 3. What if we wanted a list with 2 integers in it, like the numbers 2 and 3? Well, that would be the number 2 cons the remaining list, which would be 3 cons the empty list. And we can construct longer lists just by consing additional values to the head of the list. This notation for defining list values isn't very concise, so fortunately OCaml provides some ways we can clean this up. First, the cons operator is right associative, so all of these parentheses aren't necessary. The lists still have the correct associativity without them. Additionally, OCaml has some more familiar syntactic sugar for defining lists, where the list items are within brackets and separated by semicolons. Once we have a list, we need some way of decomposing the list to access its structure. Let's say we wanted to define a function to take a list of integers and check if the list is empty or not. We can define the function isEmpty and have it take an int list as its argument. It'll return true or false depending on whether the list is empty or not, so the function will return a bool. But now, how do we know if the list is empty or not? We need to deconstruct it to see the list's structure. And for this, we can turn back to the idea of pattern matching. We can use a match expression to match the list. But what pattern should we match the list against? For a list, there are multiple patterns we might expect, since we can construct a list using either nil or cons. For example, the list might just be the nil value for the empty list, so that's one possible pattern. Alternatively, the list might be one value, the head of the list, consed onto the remaining values, the tail of the list. So we have 2 possible patterns to check against. In the case of the first pattern, we know the list has no elements, since it matched against the nil pattern. That means the list is empty, so the function should return true here. In the case of the second pattern, we know the list has at least one element, since it has a head element. It might have more elements depending on whether the tail is empty or contains additional values, but the original list must have had at least one element to match onto this pattern. So that means the list isn't empty, and we can return false here. This function will successfully check if a list is empty or not. To clean it up a bit, since we didn't end up needing to use the variable names head or tail, we can replace them with anonymous variables that start with an underscore, or even just the underscore itself, to make clear that we didn't intend to use those names. Let's take a look at one more example for functions that work with lists. One common thing we might want to do is take the length of a list. Let's define a function for computing the length of a list. The function will take an int list as input, and it will return an int representing the list's length. As with before, we can start by matching the list. But what patterns do we match it against? Well, lists of different lengths will each have a different structure. So if the list is empty, then we could return 0. We might then try matching against lists of different sizes, which is possible too. If the list is just a single element, that's a valid pattern, and in that case we could return 1. If the list has 2 elements, that's a valid pattern too, and we could return 2. Likewise, for a 3-element list, we could return 3. But this approach is never going to work in general, since lists could be arbitrarily long. So we need to be a little more general about how we approach this problem. Let's try again. Matching against an empty list makes sense as a first step. We're still going to return 0 here. But now let's be a little more general and match against a head, abbreviated HD, and a tail, abbreviated TL for the list. What's the length of this list? We don't really know. It depends on the length of the tail. If the tail is empty, then the list has length 1. It has just the head. If the tail has one element, then the list has length 2, that one element plus the head. And in general, the length of this list is going to be one more than whatever the length of the tail is. But how could we calculate the length of the tail? Well, that's what the length function is supposed to do. So we can use recursion to recursively call the length function on the tail, adding 1 to the result. We'll also need to add a rec keyword to the function to indicate that it's recursive, and we can make the head argument anonymous since we don't use it. If you're not yet comfortable with recursion, it might seem strange that we can do this, use the length function as part of the definition of length. But this works because each time we call length, we're calling it on a smaller list. Eventually, we'll call length on the empty list, which this function knows has a length of 0. This function successfully computes the length of a list, taking advantage of pattern matching and recursion. This kind of pattern for programming ends up being an extremely common way to solve problems. It's known as structure-driven programming, and it generally involves first determining the type of the function, its arguments, and its return value, then deconstructing one or more of the arguments, and then, depending on what case it matches, constructing the output value. Let's consider a third type of structured data, records. Tuples and lists both identify their elements based on the order in which they appear. It matters which element comes first, which element comes second, and so on. Records are a way of organizing data where individual elements are instead identified by a label. For example, we might want to represent data about a person and store their first name, their last name, and their birth year. To do that, we first define a new record type. Records are an example of user-defined types, where we get to define a new type that's not already built into OCaml. There will be other examples of user-defined types we'll explore later too. Here's how we might define a new type called person. Person is a record type, and each person record will contain 3 fields: a last name, which is a string, a first name, which is a string, and a birth year, which is an int. When defining the type for a record, we use colons to separate the labels for each field from the types for each field. The whole record type is surrounded in curly braces to note that it's a record. Now that we've defined the type for a person, we can construct a person value. To construct a record value, we also use curly braces and field labels, but this time we use an equal sign after the field label to specify what value will be associated with each field. Here, we've defined a record with Alonzo Church's first name, last name, and birth year. Unlike with tuples and lists, the ordering of these fields isn't important. The 3 fields could be in any order and still be a valid person record. If we wanted to extract values from a record, we again can use pattern matching. For example, let's try to define a function that takes a person and returns their full name, their first name and last name concatenated together with a space in between. The function will accept a person type as input and return a string representing the person's full name. We can match the person against a pattern to deconstruct the record into parts. In this case, a last name, a first name, and a birth year. Again, to the left of the equal sign in the record fields here are the field labels. Those are determined when we first define the meaning of a person type. To the right of the equal sign are variable names that will represent values in our record. These variable names we can choose when pattern matching. To construct the person's full name, we can concatenate the first name, followed by a space, followed by the last name. This function works, but there are opportunities here to simplify. First, we pattern matched against all of the fields in the record, when really we were only interested in 2, the first name and the last name. The birth year isn't relevant to us when we're generating a person's full name. In a record pattern, we can instead match against only a subset of a record's fields, using an underscore to stand in for any remaining fields. So here, we can use an underscore to stand in for the remaining fields, in this case just the birth year, so that our code can make reference to only the fields we're interested in using. Next, notice that the field labels are very similar to the variable names we're using for the fields. If we had wanted to, we could have even made the variable names identical to the field labels. That kind of pattern is common enough that OCaml has another simplification in record patterns called field punning, where if the field label is the same as the variable name, then we don't need to specify the same name twice. We can just use the label alone as both the label name and the variable name. That lets us simplify our code even further. Additionally, since we're only matching the record against a single pattern, we can take advantage of the techniques we've learned to match inside of a let expression. We can avoid the need for a separate match expression and just match the person record in the argument of the full name function itself. Pattern matching is one way to extract values from a record, and it lets us get access to as many of the fields of a record as we want. If we just need to access one value from a record, there's another notation we can use, the dot notation. If we have a person variable, we can use the variable name followed by a dot, followed by the name of the field we're interested in to extract just that field. So we could instead rewrite our full name function to do no pattern matching, and just use the dot notation to access the first name and the last name from a record. We've now seen tuples, lists, and records, all examples of structured data types that group values together. They differ, though, in some important ways. Tuples and records have a fixed number of elements. As a result, their elements can have different types, since the types of those tuples and records will indicate how many elements they contain and what their types are. Lists, meanwhile, can have an arbitrary number of elements, and therefore those elements all need to be of the same type so that we know how to consistently work with any element in the list. Tuples and lists have their elements identified based on the order in which they appear, whereas records have their elements identified based on their label. All of these structured data types have their uses, and depending on what problem you're trying to solve, it may be up to you to decide what sort of data structure is the best fit for the information you're trying to represent.